I don't have much in the way of major announcements other than to say that your bolted connection homework is due next Wednesday. After today, you should have a pretty good understanding of how to do most of it. The only one that's going to be a little weird is the last one, but it's a pretty straightforward problem too. We'll handle that on Friday. I want to just jump right into it and start talking about slip critical connections. I'm going to pull up my little Google Chrome box because that sounded really technical, Google Chrome box. Because I want to pull up an image of something that's going to become relevant here in a second. Okay, up here on the board I have sort of a little table that I drew to illustrate the limit states associated with bolted connections. So with bolted connections, remember we have two types of connections that we're really assessing in here, and that's a bearing type connection and a slip critical connection. So bearing type connection, again, is one where you have the hole, you have the bolt, and it's literally bearing on the end of the plate, and that's how it's resisting the load. And so whenever you have a bolt bearing connection or bearing type connection, it must satisfy the requirements of bolt shear and bolt bearing. Slip critical connections are a little different. Okay? Slip critical connections rely on a little bit more than just the bolt coming into contact with the plate. They actually rely on the friction that you develop between the two plates of a bolted connection, right? You got plate A, you got plate B, you stick a bolt through them. As you tighten that bolt, what happens to the plates? They smack together. And so with enough oomph, if you will, on that bolt, you can start to generate a significant amount of force between those two plates. Hence, frictional resistance that comes in a slip critical connection. Now, when do you use a slip critical connection? Like, why would you use one versus a regular old bearing type connection? So bearing type connections are going to be your everyday type bolted connection in a structure. I would argue that probably most of the connections in this building are bearing type connections. So when would you use a slip critical connection? Well, typically you would use a slip critical connection in bolts that have, or in connections that have maybe weird geometry like oversized or slotted holes. One of the big ones is in any joint or any connection where the structure is going to be subjected to a fatigue load. So fatigue loads would be structures or systems where they're loaded, unloaded, loaded, unloaded, loaded, unloaded, cyclically over and over again. Can anybody think of a type of structure where that would be relevant? A bridge, exactly right. So bridges, particularly like for instance spliced connections in bridges, are all designed with slip critical bolts. And again, this was kind of the illustration I mentioned last time about the lawnmower. Like if you have a loose bolt on a lawnmower and you run the lawnmower, it'll sort of vibrate off. Well, that would be, low cycle fatigue, not very many cycles and poof, it pops off. We're in a little bit of a different scenario. Now, where's the math come from? How do we determine the capacity of a bolt according to a slip critical connection? It's right here. This is from basic physics. Everybody should remember this from physics 211, or should remember this from statics, wherever you saw it first, because I would be almost shocked if you didn't see it in both courses. Remember, if I have two objects that are exerting a normal force between them, right? So for instance, like a box on the ground, right? The box has a weight. That weight is acting on the ground, and if the ground is, let's say, level, then the weight of that box is a normal force acting on the ground, right? Well, we can define a coefficient of static friction between the box and the ground, and so the coefficient of static friction times the normal force will tell us what force we must overcome in order to get that box moving, right? Like if you're trying to move your refrigerator across your kitchen, it's a function of how heavy your refrigerator is and what's the coefficient of friction between your refrigerator and the floor, right? So it's basically the same idea. If we can determine the frictional coefficient between two plates of steel and the amount of force that we apply to suck those plates together, the bolt pretension, if you will, well, there's your nominal capacity according to a slip critical connection. It's that simple. Now, how do we do this in structural steel design? Well, the capacity of a slip critical bolt is all a function of really this term, this minimum bolt pretension. Okay. In other words, I have a plate, I have a bolt stuck through them. Plates get sandwiched together depending upon how tight the bolt is, right? So would a fair statement be the tighter that bolt, the more force between those two plates? Would that be a fair statement? So how tight is tight enough? Well, what we do in structural engineering is we have a series of prescribed methods that we use to achieve that required torque, or to achieve what we call that minimum bolt pretension between those bolts. It starts off by getting the bolts what are called snug tight, and then we apply one of these prescribed methods. So what do I mean by snug tight? Snug tight is what you would attain with, the few hits of an impact wrench, or what we would define as the full effort of an iron worker. It's not a super exact science, and you're going to see why here. See what happens with this here in a second. But once you get snug tight, you then apply one of the prescribed methods to achieve that specified pretension. So if we're going to have a slip critical connection, we've got to achieve that degree of pretension. Now I'm curious, how many of you, have any of you worked on like DOH or construction jobs or whatnot over the summer? Have you ever been on a job where they were bolting steel girders together, like they were splicing them together? Has anybody seen that? When they bolted them together, did you see them put these little chalk lines on for the bolts, where they would have a chalk line on the girder and on the bolt, and they would turn it to where they matched? Or did that? You're shaking your head. Yes, you've seen that. Did you see that on yours? What'd they do? Or
I really don't remember what they did. I think they just tightened them up and then.
You might see what they did here in a second, because there's a couple ways to achieve that pretension.
They also, after they done that, though, they had a wrench that had like the actual torque on it.
Yeah, a calibrated wrench. Yeah. So they might have used that as well. We're gonna talk about that here in a second. There's a couple of ways to achieve this pretension after it's snug tight. Probably one of the most common is what's called the turn of the nut method, and that's the one that I'm talking about with the marks. You can also use a calibrated wrench. Lost my battery cover. You can use what are called twist-off control bolts. You can use DTIs, and you'll see what all these are here in a second. So let me show you what the turn of the nut method is. This is probably one of the most common methods to get that direct pretension after it's snug tight. So what will happen is you'll go on and you'll place chalk marks once it's snug tight on, let's say, the bolt, the plate, and then the nut. And what will happen is, okay, you look up in the spec, maybe it's a third of a turn. So you go a third of a turn and place another chalk mark here, and then you effort that bolt or effort that nut such that once it's turned, they wind up, and that'll tell you that, okay, you've met that appropriate pretension. Now, what happens inside the connection is, you've already got it snug tight. Okay. So if you turn that nut, what's happening? If it's already snug tight, what is actually happening? Well, by turning that nut past snug tight, what you're doing is you're taking the bolt and you're actually elongating it, right? Because inside the connection, that bolt is actually getting longer, because if you turn this out, that thing's going to stick out, all right? What that elongation is going to do, the fact that the bolt is getting longer, that is going to apply a force to those plates. If that doesn't make a lot of sense, or if that's hard to visualize, think about this. Say I have a rubber band in my hand. Okay, if I take that rubber band and I make it longer, what is it doing to my thumbs? Like if I have it right here and I take it and I make it longer, what's it doing to my thumbs? It's wanting to suck my thumbs back in, right? By making it longer, you're actually applying that internal force. This is one of the ways that we do that. Another one of the ways we do that is we use a calibrated wrench. If they're ever using a calibrated wrench on the site, you'll probably see one of these. Did you happen to see one of these on site? They might have had it in the back or something, I don't know. This is what's called a Skidmore-Wilhelm. Basically, if you want to describe what a Skidmore-Wilhelm is, it's basically like a super duper hyper accurate bathroom scale. You put a bolt in between, and then you attach your wrench and you start tightening it, and what the Skidmore-Wilhelm will do will read the amount of torque that your wrench is putting on the bolt, and then once you've calibrated it, you can then go and start using that bolt or using that wrench to start tightening those bolts. One of the rules is that if you can go and use that wrench to your heart's content, but as soon as you stop working and go back to work again, you have to go back and recalibrate. So, you are maybe under a little bit of motivation to keep on trucking on. Now, this one is a system that's started to gain quite a bit of popularity in the last few years, and these are what are called twist-off control bolts. This is one of the motivations in the spec for, instead of dealing with A325 bolts or A490 bolts, this is one of the motivations for saying, okay, we have Group A and Group B. Because these technically fall under a different ASTM spec, even though they might behave the same mechanically as a Group A or a Group B bolt or something like that. But basically the way it works is, so you have this wrench, and what it does is it has two chucks that sort of spin in the opposite direction of each other. One of them takes the nut and, let's say, spins it this way, and one of them grabs the bolt and spins it the other way. And once you achieve your required, prescribed tension, that little splined end, that little nub on the end of the bolt chucks off. And so if you look at a splice connection, you'll see, like for instance, this one they haven't tightened yet, this one they haven't tightened yet, but this one they've already tightened and the end is chucked off, and this one the end is chucked off, and you can see they're doing that. Did you see those on this?
I think those were.
Yeah. These are really, really slick because you don't need a wrench on the other side. Like if you've ever tightened anything, if you ever tightened up bolts, you need a wrench over here and a wrench over there to tighten, right? Well, this one device grabs the bolt and the nut, so you don't have to do that. You just sit up and whoop, it takes care of it. A little pricier, but a lot faster on site. Another method that's used to achieve the appropriate pretension is what's called a DTI. A DTI stands for a direct tension indicator, and it's basically a super fancy washer. The washers have these little nubs on the top of it, and so as you tighten the bolt, the nubs mash down, and once you achieve a required gap, or once this gap hits a certain threshold, then you know you've hit the required pretension. I've even seen some of these DTIs where the washer has this little pocket and has this orange goop in it, and they tighten it up, and then once you hit a certain pretension, the goop comes out, and then once you see the goop coming out, you're like, oh, okay, I hit my pretension. So there's oodles and oodles of different ways to do this. I'd say probably this is starting to become one of the most common methods nowadays, just because it's simple. You just one wrench and it takes care of it. And it's easy for an inspector to come out and check too, because once the ends have all come off, you know you're good. Any questions? Okay, now, like I said, the way that you compute the capacity, again, it goes back to basic physics, okay? You need a coefficient of friction and a normal force, okay? Coefficient of friction, normal force, okay? So we have mu, which is our slip coefficient. We have T sub B, which is our minimum fastener pretension. That's the normal force generated on a per bolt basis, okay? The rest of the numbers here, the rest of the terms are just adjustments to that base expression from physics, like a filler plate factor, this D sub U factor, which we're going to talk about, and then the number of slip planes. But it all comes back to just basic physics. Now, our phi value is actually 1. This is probably one of the only instances where phi is not 0.75 or 0.9. It's actually 1. There's one other instance that I can think of that we'll deal with, and that's when we're looking at shear in beams. But by and large, this is, I think, one of the only ones we're going to deal with in here. The reason why we're using phi equals 1 is because phi is 1 when you're dealing with a standard bolt hole. If you're dealing with slotted bolt holes or oversized holes, phi changes. It goes to like either 0.85 or 0.75. But we're just going to be dealing with standard holes in here. So let's talk about each of these terms and ultimately how you'll really never have to compute with any of them because they're really, really simple. But you'll see where I'm going. Okay, so mu. Mu is our slip coefficient, but that's basically just from physics. It's our coefficient of static friction. Okay, so what that's going to depend on is I'm taking plate A, plate B, slapping them together, sticking a bolt through them. So mu is going to depend on the surface between those plates, right? What's the condition of that surface? We have a name for that in structural engineering. We call that the FAME surface. So if you ever hear me use that term, FAME surface, what I mean is that surface between plates in a bolted connection where you're generating a frictional force. And that depends on the surface condition. So, for instance, if you have blast clean steel versus clean mill scale, that's going to change the coefficient of static friction. So clean mill scale is generally just what comes straight from the steel mill, and blast clean is going to be something that's sandblasted. So if you sandblast it, you can get a little bit more frictional capacity. Typically what you would do as a designer is, unless it's stated otherwise, you would assume class A. Now, one thing I will tell you is, and this is, I'm going a little bit off on a tangent here, but I think this is kind of important. These values are what are delineated by this, okay? For instance, if you're designing bridges, you're using a different specification. The concepts and the theory is exactly the same, but maybe the bridge spec says, well, we don't use 0.3, we use 0.32 or 0.33 or whatever. That's something that can happen a little bit in our world in structural engineering, is that, you know, the bridge spec and the building spec might be a little different in terms of what values to use, but the theory is exactly the same. We're going to use 0.3 in here unless it's stated otherwise, but I just wanted to throw that out there. Okay, so we're going to take each of these terms one at a time. So that's mu. What about this du term? Okay, now, this is one of those times where Dr. Mike puts on his second exam, why is du equals 1.13? And you're like, I don't remember, so I'm going to say it's a factor of safety because I think that sounds good, okay? If there's any case where that would be wrong, it would be here, okay? Let's think about what a factor of safety does. A factor of safety, so here's my table, right? Table can hold up 400 pounds before it cracks. So if I have a factor of safety of 2, my usable capacity is 200 pounds. I would reduce the capacity, right? That's what a factor of safety does. Well, look what it's doing here. du is 1.13, so this value is actually increasing the capacity. So to say it's a factor of safety is wrong. It is absolutely wrong. Okay? So what is it doing? Well, remember all those prescribed methods that I talked about? The direct tension indicator, the twist-off control bolts, the turn of the nut, all that stuff? Do you think those things are super exact, laser-focused scientific methods? No, they're not. There's going to be a difference between the amount of bolt pretension that we specify and what we actually get in the field. The benefit to those methods is that they tend to generate more pretension that we need. What is this d sub u value? It is the difference, it is the ratio between how much pretension we need to generate from a design standpoint versus how much we actually get. And on average, using these prescribed methods, we get about 13% more pretension in the field than what the spec specifies. Okay? That's what d sub u is. It's taking these prescribed methods and applying a little bit of a dose of reality to it. In reality, we end up getting more pretension in the field than we get than what we specify. And how much more? About 13% more. Yes?
You say 13% on average more. Would it not be more safe just to assume one case of plate?
That's a great question. And so that comes to right here. Sorry. Bless you. Using one, if you want to use that, that's fine. One of the things about the spec that is stated is that it's pretty much equal to 1.13 according to the spec, but the spec does have a provision that states that the EOR can use a different value if they feel justified. Pop quiz, what do I mean by EOR? Anybody know? Anybody heard that term before? The engineer of record. He or she who is stamping the drawings. So the EOR can use a different value if they feel it's justified. That's really rarely done in practice. Again, keep in mind, usually when you're developing specs like this 13% is the floor so much of that data. You're probably getting way more pretension than that. Usually what an EOR record or an engineered record might want to do is use a higher value, not a lower value. Now, if you were concerned about it from a safety standpoint, if you wanted to use a lower value, you could. Keep in mind, though, that when you're doing that, what you're telling a client is, the spec tells me to use 1.13, but I'm using 1, knowing it's going to cost you more money to build this system. You see what I mean? I mean, 1.13 is a perfectly safe value to use. And when we talk about safety, keep in mind, you're not using raw loads. You're taking your dead load and you're upping it by 20%. You're taking your live load and you're upping it by 60%. So there's a lot of safety built into the spec, right? That's why we take, we do 1.2 dead plus 1.6 live. We up the live loads 60% more, right? You have an element that has 100 kips in live load. We're saying design it for 160. That's a big deal, So that would be a really valid point to mention. Does that make sense? Is everybody else okay with that? Okay. Now, T sub B, this is the minimum bolt pretension. If you actually go to chapter J, it's in there, so you can, this is a lookup. It's about 70% of the minimum tensile strength of the bolt rounded to the nearest kip. But you're going to see here in a second how this guide isn't even all that necessary, okay? But it's there in the spec if you want to take a look at it. It's on page 16.1-119. Again, there's a lot of stuff in chapter J, okay? All right. And obviously there's different values for group A bolts versus group B bolts, so on and so forth. Okay. If there's one thing I want to do on these slides in the future, I'd like to improve this image, because this image comes from the manual, but I don't really think it's all that clear, so this is my Google reference. Okay, so one of the most common connections that we utilize in structural engineering, particularly of bridges, is what's called a field splice, okay? So what's going on with a field splice is you have a girder that, let's say you have a bridge that's 300 foot long. You do not bring a 300 foot long piece of steel down I-64. What you do is you bring it in pieces and you connect it together. Now, we are doing basic bolted connection design in this course. The design of a spliced connection is very intricate because you have to design it for axial load, for shear, bending, there's block shear. Every connection related issue you could think of is in this connection. So they're very, very difficult to design. Now, one of the things so that would be my first point. The second point I would say is one of the things that your goal is in a spliced connection is to connect two different pieces of a girder together, girder A to girder B. But that does not mean that they have to be the same size girder. Like for example, let's say you have a beam, a bridge that's like this. The moment diagram is probably going to look something about like that, right? More bending in the middle than there is on the ends. Now let's say you have a splice right there. Maybe what you want to do is have a beam that's, let's say, this size, and then at that connection, connect that with a beam that's a little bit bigger, right? Because you need a bigger beam in the middle than you do on the ends, right? So on your splice connection, what you might have is you might have thicker flanges on one side than you do on the other. Does that make sense? So if you zoom in, what you can see right here, this is where the flanges are connected, and see how you've got this thick flange here, but over here it's a little bit thinner. Everybody see that? So let's say this is let's say this is 1 inch, and let's say this is 3/4. Well, if you want that to be flat, what do? You stick you a little 1/4 inch filler plate in here so that when you connect them, 1 inches comes flat. Does that make sense? That's what a filler plate is. A filler plate is when you're trying to connect one element to another and they're of different thicknesses. You put another plate in there so that the thicknesses match up. Does that make sense? Now, unless the clarity of this image is a bit off, that looks like a single filler plate. You could have multiple filler plates, and the only time that would ever really happen is if you're trying to splice like a 19/64" thick plate with a 1/2" plate. Maybe you can't get that one plate. Maybe you need like, 160, like a 64th, and then an 1/8, or some weird situation. If you ever had multiple filler plates in a slip critical connection, you would use a different H sub F, but in this class, we're never going to do that. So we're always going to take our filler factor to be 1. And finally, our N sub S, which is the number of slip planes, that's just the number of shear planes. It's the same thing, whether it's single shear, double shear, just single slip or double slip. I have one final thing I want to show you because we're running out of time. I want everybody to go back to this table right here. This is the shear strength table. So you should be at table 7-1. All right? Now turn the page. This is table 7-3. Okay? This is the table that lists the slip capacity of a single bolt. Now, if you look, there's 2 tables, one on the left, one on the right. The one on the left is for group A bolts. The one on the right is for group B bolts. Okay? Another thing about this table, these tables both all assume Class A fang surfaces. If you ever had a Class B, you would just multiply the whatever you get in this table by 1.67, because that's 0.5 over 0.3. We're only going to be using the standard size holes. So for instance, if you had a 3/4 inch bolt, single slip group A, its slip capacity is like 9.49 kips. Everybody see that? So 3/4 inches in diameter, single slip group A, 9.49. Does everybody see that? What we'll do next time, because we're running short on time, we're going to design a connection that's slip critical. It'll be a really quick problem. And then after that, we're going to ask about that. Because this connection is experiencing what's called combined loading, because it's not experiencing shear, it's not experiencing tension, it's experiencing both. Okay? You all can handle a bolted connection in shear. We've been doing that this whole time. You can handle a bolted connection in tension because that's just a threaded rod problem. But what if it's both? What if it's seeing a combination of shear and tension? Okay? That's a discussion. Not hard, but we've got to talk about that. That's all I got, everybody. I know this was a short lecture, but given the concrete design folks' experiences, I don't think you're complaining. That's all I got.